Class, in this toolbox, we're going to continue talking about functions, but we're really going to talk about some of the basic mathematical functions that we often use to describe natural phenomena. These include things like linear functions, exponential and logarithmic functions, and wave functions like sine and cosine. These should all be functions that you're familiar with from some of your earlier courses, but it's always good to get a reminder. We'll also talk about how we can put different functions together. First, we'll talk about linear and polynomial functions. We're all familiar with linear functions. Linear functions are any function that graphs to a straight line. Linear functions have no exponents or powers associated with the input variables. The graph on the right is, of course, an example of a linear function. Linear functions are actually one example of a polynomial function. A polynomial function is a function that has exponents on the inputs to the function, but includes only non-negative exponents. Polynomial functions include quadratics, like that shown on the figure here. They also include cubic functions, like this one, and quartic functions, like this one. We refer to polynomial functions by the highest exponent or power in the equation. For instance, an equation that has x cubed plus x squared plus x would be referred to as a third-degree polynomial, because the highest exponent is 3 in the cubed term. The basic equation for a polynomial is shown at the bottom. F of x equals an times x to the n plus an minus 1 times x to the n minus 1 plus ... depending on how large n is, plus a2 times x squared plus a1 times x plus a0. The letters a are all referred to as the coefficients of the polynomial. Note that we would refer to this function as an nth degree polynomial because n is the largest exponent in the polynomial. For instance, if n was 7, we would be raising x to the 7th power, and it would be a 7th degree polynomial. Next, we're going to talk about exponential functions. Consider for a moment a population of rabbits. They breed like, well, rabbits. So if we start with one rabbit, we'll soon have 2 rabbits, then 4, then 8, 16, 32, 64, 128, until the rabbits have completely overrun our backyard. So let's think about this function. We can put together a table of the number of rabbits as a function of the generation number. The first generation has 2 rabbits. The second has 4, then 8, 16, 32, 64, 128. We could also graph this data. We start with 1 rabbit, then 2 after the first generation, then 4, 8, 16, 32, 64, 128. We can see that the population grows quickly. This rapid population growth can be quantified using an exponential function. An exponential function is a function in which the input variable is in the exponent of the equation. We could write this equation as f of x equals 2 to the x. Now let's check to make sure that this actually fits our data. 2 raised to the first power is just 2, so it is equal to 2. That checks out. 2 raised to the second power equals 2 times 2, so that's equal to 4, and that checks out. 2 raised to the third power means 3 2's multiplied together, so that equals 8. 2 to the fourth power equals 2 times 2 times 2 times 2, so that equals 16. 2 to the fifth power is 5 2's multiplied together, so that's 32. 2 to the sixth power is 6 2's and hence 64. 2 to the seventh power is 7 2's and hence 128. Exponential functions are very useful for quantifying the growth of populations, but also for many other things, like computing compound interest. Exponential functions always take the form f of x equals a times b raised to the power of x. Note that the independent variable, which is the input to the function, is always in the exponent of the function. We refer to b in this equation as the base, and we refer to x as the exponent. There are some important properties of exponential functions that you should be aware of. The first is that b raised to the x is equal to b times b raised to the x minus 1. Let's take a moment to see why this works. Let's say that b is 7 and x is 4. In this case, we're asking if 7 to the fourth power equals 7 times 7 to the third power. While 7 to the fourth power is 7 times 7 times 7 times 7, is that equal to 7 times 7 to the third power, which is 7 times 7 times 7? Of course it is. So that makes sense. Now let's look at the second equation. It states that b raised to the x power equals b raised to the x plus 1 power divided by b. Let's see if this works. This time we'll choose 5 for b and we'll choose 3 for x. So we're going to ask the question, does 5 to the third power equal 5 to the fourth power divided by 5? Hopefully you can see that 5 times 5 times 5 equals 5 times 5 times 5 times 5 divided by 5. Let's now use these properties to understand another important property of exponential functions. We all understand that b raised to the x power means multiplying b times itself x times. For instance, if we had b to the 7th power, we write down 7 b's and multiply them all together. Nice and simple. But what if x is 0 or even negative? That's much less intuitive. How do we multiply 0 7s together? Or negative 2 7s? Well, let's focus on that second equation and think about what we could do. We'll start by plugging in 7 for our base. We want to figure out what 7 to the 0th power is, so let's plug in 0 for x in this equation. We now see that 7 to the 0th power is equal to 7 to the 0 plus 1 divided by 7. We can now see that 7 to the 0th power will be equal to 7 to the 1 divided by 7. And of course, this is just 7 divided by 7, which equals 1. Hopefully, you can look at the analysis we just did and realize that it didn't matter what we put in for b. We used 7 here, but we could have used 5 or 6 or 1023, and we would still have gotten an answer of 1. This leads us to a general property. Any positive base raised to an exponent of 0 is equal to 1. But this isn't the only thing that we care about. We were also interested in calculating 7 to the negative 2. So let's continue. Using our same equation, we can calculate that 7 raised to the negative 1 equals 7 to the 0 divided by 7. So 7 to the negative 1 equals 1 over 7. Let's do this one more time. 7 to the negative 2 plus 1 is of course equal to 7 to the negative 1 divided by 7. And we just calculated that 7 to the negative 1 equals 1/7. So we can substitute that in, and we find that 7 to the negative 2 is equal to 1/7 divided by 7. Using our same equation, we can calculate that 7 raised to the negative 1 equals 7 to the we can calculate that 7 to the negative 2 is going to be overall equal to 1 over 7 squared. Generalizing this idea, we can see that b to the negative x is equal to 1 over b to the x. This general equation allows us to calculate the value of any base raised to any negative power. So why is it that we would want to use a negative exponential? Well, let's think about exponential decay. Radioactive elements decay away at a fixed rate, such that half of them disappear over a period of time equal to the half-life of the isotope. Let's say that we're working for the Department of Energy, and they're trying to figure out what to do about some radioactive waste left over from a nuclear power plant. We need to figure out how long it will take for that nuclear waste to decay away. We can apply what we've learned about negative exponentials and write the function a of n equals a0 times 2 to the negative n. In this equation, a of n is the activity of the radioactive material as a function of the number of half-lives that have passed. A0 is the initial activity of the radioactive material, and n is the number of half-lives that have passed. Thus, if we want to know how much radioactive material is left after 4 half-lives have passed, we can plug in 4 for n. We can thus use the equation to the left to figure out what 2 to the negative 4 is, and we see that it is 1 divided by 2 to the 4th power. This, of course, is equal to 1/16. So we can tell the Department of Energy that 1/16 of the radioactive material will remain after 4 half-lives. If we graph that negative exponential, we can see the proportion of the radioactivity that will remain as a function of the number of half-lives that have passed. On this slide, I have a few different examples of exponential functions. One for rabbit population size, as a function of the number of generations that have passed. The next is for radioactive decay. And the third approximates human population growth over the past 170 years. In the last lecture, we talked about the inverse of a function. The inverse of a function is the function that takes the output of one function and then gives you back the input of that function. We discussed the fact that not all functions have a well-defined inverse. However, we basically decided that anytime you can draw a horizontal line through a function and only hit that function once, you should be able to find an inverse for that function. Looking at these examples of exponential functions, it's pretty clear that that is true. Anywhere you draw your line, from any output value, you only have one potential input value. This means that exponential functions should have a well-defined inverse function. That inverse function is the logarithmic function, and it's the next important type of elementary function that we need to talk about. A logarithmic function is defined as the calculation of the exponent in the exponential equation y equals b to the x. So basically, if I give you y and b in that equation, you need to tell me what x is, and you use the logarithmic function to do that. A logarithm is the same thing as finding the exponent to which the base must be raised to get the desired value. So let's think about this using our function boxes again. Our first function is an exponential function, g of x equals 2 to the x. If you give that function the number 3, it will spit out 2 cubed equals 8. If you give it 4, it will calculate 2 raised to the 4th power and spit out 16. Now we want an inverse function that takes in the 8 and spit backs out a 3, and takes in a 16 and spits back out a 4. Because remember that whatever goes into the first function as the input should come back out as the output once you've applied the original function and then the inverse function. As I said, we define the inverse function of an exponential as a logarithmic function. So we know that g inverse of x must be a logarithmic function. And we write it using the nomenclature log base 2 of x. Log base 2 of x answers the question, if I give you some number, what exponent do you need to put on the number 2 in order to give me my number? For instance, if I give you 16, what x do you have to put on 2 to get 16? Let's work through the math for a moment to look at what the logarithmic function typically looks like. We'll start with the exponential function g of x equals 2 to the x again, simply because this is one of the easiest exponentials for us to calculate. We've graphed this before, so we know what it basically looks like. Now let's compute some points and also plot them onto our inverse function graph. First we'll choose x equals 0. We decided before that anything raised to the 0 power is 1, so we'll plug in g of 0 equals 1, and if g of 0 equals 1, then g inverse of 1 equals 0. Next let's pick x equals 1. G of 1 equals 2 to the 1, so it is equal to 2. If g of 1 equals 2, then g inverse of 2 equals 1. So let's stick that on the inverse graph. Next we'll try x equals 2. G of 2 equals 4, so g inverse of 4 equals 2. Next we'll try x equals 3. G of 3 equals 2 cubed, which is 8. If g of 3 equals 8, then g inverse of 8 equals 3. We'll plug in one more set of values. G of 4 equals 2 raised to the 4th power, which is 16. If g of 4 equals 16, then g inverse of 16 equals 4. Okay, that's enough points for us to start to get the shape of the logarithmic function. I'll now fill in the rest of the line. This is the general shape of a logarithm. It increases rapidly in the beginning, but then begins to level off a lot. Just so we're clear, logarithms are not generally something that we calculate ourselves. With the exception of a few values, like for instance those ones that we just plotted on the figure, I almost always just plug logarithms into a calculator or a computer to solve. However, I use logarithms all the time in my research, so I just want to take another couple minutes to make sure that we're clear on them. This is the general shape of a logarithm. If we have an exponent of b to the x, where b is the x, the inverse of that is log base b of x, written in the notation on the right. So let's say you want to know what the log base b of x is. You can think of this as solving the question, what is x if y equals b raised to the x power? Let's go through one example. We'll calculate log base 10 of 1000. This is equivalent to asking what the exponent is in the equation 1000 equals b to the x. Hopefully you can guess for yourself what this should be. 1000 equals 10 times 10 times 10, so the exponent is 3. If the exponent is 3 in the equation on the left, then we've solved the logarithm. So that's how logarithms work. Keep in mind that the base in the logarithm can be just about anything. We've already used 2 as the base, but you can use any number that you want. There are 2 numbers that are very commonly used in the base. One of them is 10. Log 10 is used so often that sometimes people will just assume that if there is no number written out, you should just assume that it is log base 10. However, I would definitely encourage you to always write out log 10 so that you never create confusion. The other number that is very commonly used is e. E is a special number in math, like pi. E equals 2.7183. Log base e is used so frequently that we have a special name for it. We refer to log base e as the natural logarithm, and we write it ln of x. The reason for this special status for the value 2.7183 is its relation to exponential growth. When calculating exponential growth, the equation for exponential growth is p of t, so that refers to the population size as a function of time, equals p of 0, which means the population size at time 0, times e to the lambda t, where lambda is the growth rate and t is time. Note that from what we know about logarithms, if p of t equals p of 0 times e to the lambda times t, then we can solve this equation for the growth rate by first dividing by p of 0 and then taking the natural logarithm and dividing by t. This is a really important equation in biology and ecology because it allows us to calculate the growth rate of a population if we know its initial abundance and its abundance at some later point in time. Note how important e is in this equation. Later in this course, we'll come back to e and we'll discuss why it is that e has this special place in math and biology, ecology, geology, meteorology, economics, really anything that involves math and growth or decay over time. The other reason that I constantly use logarithms in my research is for logarithmic transformations. This graph shows a graph of the function f of x equals log base 10 of x. Notice that it basically compresses the input. If you give it an input of 1, it will give you a value of 0. If you give it an input of 10, it'll give you an input of 1. If you give it 100, you get 2. Give it 1,000, you get 3. Give it 10,000, you get 4. So it compresses your data. Consider this data from my student Becca Morrow's paper. Becca was looking at the relationship between phytoplankton growth on the y-axis and light on the x-axis. And in this figure, we were asking the question, does the growth rate versus light relationship vary between 3 different regions: nutrient-limited regions, oceanic regions, and upwelling regions? If you look at this data, however, it's really very hard to make much sense out of it because so much of the data is clustered at a light level of less than 50 microeinsteins per meter squared per day. This reflects a fundamental issue with looking at a lot of environmental data. Most of the values are actually quite low, but we have some data that is quite a bit higher. For instance, in this graph, more than half of the points are compressed in that small box on the left, while our eyes can really only discern the patterns associated with the far fewer points on the right side of the graph. So what can we do about this? We can log transform the data. Consider what that would do. The log 10 transformation of 100 is 2, and the log 10 transformation of 1,000 is 3. So it would take the points between 100 and 1,000 and put them in the space between 2 and 3. Meanwhile, the log 10 transformation of 10 is 1, and the log 10 transformation of 100 is 2. So all the points between 10 and 100 would get moved to between 1 and 2. So as much space would be given to the 10 to 100 points as would be given to the 100 to 1,000 points. Let's take a look at what the log base 10 transformed data would look like. This is what we call a log-log plot. The data going into both the x and y axis has been log base 10 transformed. It compresses all the data so that we can see it clearly. Now instead of the data going from 0.1 to 1,000, with most of the data stuck in the region less than 50, all of the data has been spread out from -1 to 3 on the x-axis. Often, to make the values easier to see for our readers, we'll show the non-transformed data on the axes labels like this. So you can now see that the x-axis data actually spans almost 4 orders of magnitude, from 0.1 to 1,000, and you can start to clearly see the relationship between light and growth rate. Plotting this data using a log-log plot allowed us to clearly see the relationships and then fit a function to the data. By doing this, we were able to determine that there was no statistically significant difference in the relationships between growth and light in the 3 different regions. Another group of elementary functions that we use constantly are trigonometric functions. Trigonometric functions are related to the angle of a right-angled triangle and the ratio of the 2 side lengths of that same triangle. For instance, the sine function shown here is defined as the ratio of the opposite side of a triangle to the hypotenuse as a function of the angle of one of the vertices of that triangle. I'm not going to go into the details of the trigonometric functions at the moment because we have an upcoming toolbox devoted to them. However, they're a very important class of functions that will be useful for this week's homework, so I wanted to introduce them here. We use them a lot because they are periodic wave functions. The sine function repeats itself with a period of 2 pi. This means that sine of 0 equals sine of 2 pi equals sine of 4 pi equals sine of 6 pi, etc. Sine functions are very useful for graphing a lot of environmental data. For instance, we could estimate the average monthly temperature in Tallahassee using the function t of y equals sine of y minus 0.25 times 2 pi times 13 plus 68. This gives us something approaching the cyclic periodicity that we actually feel in seasonal temperature with cold winters and warm summers. If we had a need to be more precise with our data, instead of looking at average monthly temperatures, we could write a new function, f of y, that equals sine of y minus 0.25 times 2 times pi times 13 plus 68, plus another sine function, this time the sine of x times 365 times 2 pi times 10. This additional term adds in the cyclical pattern of warmer temperatures during the day and colder temperatures at night. This graph only now looks at 1 year's worth of data, but you can clearly see that we have the seasonal cycle in there, but also the ups and downs in temperature for every single day. And we get this graph by simply adding 2 sine functions together. The absolute value function is another function that is often quite useful. For instance, let's say you are developing a new pH meter to measure the pH of seawater on a whole bunch of autonomous gliders that you're going to deploy all over the oceans to monitor ocean acidification. One really important thing that you might want to figure out is the precision of your instrument. After all, you need to know if the differences found by 2 different gliders are real, or if you simply have poor precision between your 2 gliders. So to calculate the precision, you might put a whole bunch of your new pH meters into a pH buffer. Remember that since your goal is to determine the precision of your instrument, not the accuracy, you're going to look at how far apart your measurements are, not how close they are to the true value. Okay, let's say you've made measurements in the same standard with 5 of your pH meters. Now you want to compare them to see how far apart they are. So you calculate the paired differences between each of your measurements. Measurement 1 minus measurement 2 equals 8.2 minus 8.1, so that is 0.1. Measurement 1 minus measurement 3 is equal to 0. Measurement 1 minus measurement 4 is equal to 0.2. You go through and you calculate all these differences and you put them in this table here. Now, if you take the arithmetic mean of these values to try and figure out what the typical precision was, you'd calculate a value of negative 0.05. But if we look at that data, that doesn't actually make sense for our precision. Most of our measurements were farther apart than that 0.05 value. In fact, only one pair of measurements is closer than that. That's because the measurements where the first measurement was larger than the second measurement are largely canceled out by the measurements where the second measurement was larger than the first one. Instead, it makes much more sense to calculate the precision by first taking the absolute value of the differences between the measurements, which basically means getting rid of all of the negative signs. When we now take the arithmetic mean of the absolute value, we get a much more realistic estimate of the precision with a value of 0.13. The last thing that we're going to talk about in this toolbox is manipulation of functions. Don't forget that the language of functions allows us to combine different functions in many ways. Consider two of the basic functions that we've discussed. Let's define f of x as log base 10 of x and define g of x as sine of x. If we want to, we can now define a third function, h of x equals f of x plus g of x. In this way, we are adding two functions together to create a third function. If we graph h of x, we'll now find something that is the additive of a logarithmic and a sinusoidal function. Instead of adding the two functions, we could multiply them by each other to create a new function, j of x. If we graph j of x, we find a wave function that grows in amplitude over time. And as we discussed before, we can also take a function of a function. If we define k of x as f of g of x, we now get this strange looking periodic function. Also, take a moment to note that f of g of x is not the same thing as g of f of x. If we define m of x as g of f of x and then graph it, we find that f of g of x and g of f of x look very, very different. Always keep that in mind. When adding or multiplying functions, it doesn't really matter what order you use. However, when you're taking the function of a function, order definitely matters. When using these different elementary functions that we've talked about in this lecture, and adding, subtracting, multiplying, or dividing the functions, or taking functions within functions, there are infinitely many potential functions that you can come up with to express relationships in natural phenomena. Okay, that's it for this toolbox. Don't forget to take the mini quiz on Canvas before class.